This is 3.5. It's called infinite limits, or limits to infinity and beyond. Our objectives is to just understand what happens when we're trying to evaluate a limit and there really seems to be no bounds to it. So it's not actually approaching any specific y value. So the other objective is to stay awake, Stephen, because this is going to be really quick. It's going to be so quick. Alright, so just a quick reminder of what limits are. When we're looking at a limit and trying to evaluate, this is just our parent reciprocal function or inverse function. And if I were to ask you to evaluate the limit, we're saying, well, let's look at the y values as x approaches a certain value. So I'm asking you to look at as x approaches 0 here. And if you were to just look straight at this graph, I hope you could see that, hey, as I'm getting closer and closer from the left, so we're looking at from the left, it's going towards, well, it's basically shooting downwards. And this one's shooting upwards as we're approaching it from the right. So you can look at that graph, or that numerical chart as well. So when you're looking at these, you're saying, hey, the left and the right do not agree. I hope you can quickly conclude that the limit at x equals 0 of our function 1 over x does not exist. So keep in mind, this is just, for example, 1/2. So when you're saying, hey, let's plug this 0.5 or this 1/2 into our function to see what is our y value doing, it's going to be 1 over 1/2, which when you take the reciprocal of it, 1 times 2 instead, you're going to get the 2. And then these are becoming smaller and smaller values, you know. So what's happening over here? Well, when you divide by smaller and smaller numbers, it actually you're multiplying by a larger number. So 1 times the reciprocal of 1/10 would be 10. So you can see how these are shooting up. So, and then likewise for the negative values, it would just be, these would be shooting down. So when we're looking at these types of graphs and the y seems so elusive, there goes the y. The y, I mean, you can't get y. It never achieves an actual value. It's just shooting up or it's shooting down. And this is what we call infinite limits. So how do you approach that type of scenario? Well, you just say exactly what it's doing. It's either going up without bounds. So we're going to say, well, the limit is going to be equal to infinity. Or it's going down without bounds. And so in which case you're going to be saying, well, that function, as we approach that certain value, so as we were approaching that value from the left, in that past example of the inverse function, well, it was going down without bounds. We would just have to say it was going towards negative infinity. As we were approaching the value x equals 0 from the right hand side, so we would have said, well, this limit I can evaluate it at infinity, right? Because it was going up without any bounds. If you wanted to try it, plug in a couple more values, but you're never going to achieve a certain value that it's tending towards. Alright, vertical asymptotes then. This is what leads us to the idea of a vertical asymptote. If the scenario is occurring where this value is just increasing and going towards infinity or negative infinity, what we have is a vertical asymptote. So let's say that I were to take this function h of x and actually, which is equal to this rational function, and try to evaluate the limit as x approaches c. So let's evaluate this rational function. So of course the first thing that you would want to try is to plug or directly substitute in, so we would get f of c over g of c, whatever those two functions may be. And this is the thing, if the bottom is equal to 0 and not the top, so anything, the top could be anything, whoops, that's a y, anything over 0, then what we're getting is by definition a vertical asymptote. Careful, the top doesn't equal 0. This is something that we would call undefined here. If we plugged in that c value and we got something over 0, this is what we would call undefined. If we plugged in that c into our function and we got 0 over 0, this is that indeterminate form. This is where you're going to want to try some manipulations because it's not an asymptote. This is most likely a hole. So here is by definition what an asymptote is now. This is the formal definition. Before we approach just as a vertical line that your function increases but never crosses, or increases or decreases infinitely. This should be also decreases infinitely but never crosses. Up here, this is the more formal definition now. As we approach from the left or the right, that x value, if it's going towards infinity or going towards negative infinity, then that line at that value that we're approaching is a vertical asymptote. Alright, so our approach to these problems is to always factor your polynomials if you can, right? So that's the first step, because if you can reduce by crossing off bottom and top common factors, then what you have is what we call a removable discontinuity. Okay, these are what we have, these are holes, and the limit can be evaluated there. So remember, when we have graphs like this where you're approaching that hole, you can calculate the limit, you can evaluate the limit there. Alright, but if you do, once you've done this reduction of your, or simplifying of your original function, and you still have factors on the bottom that can be set equal to 0, those factors are what would create an undefined scenario, and these are where we have asymptotes. They are non-removable discontinuities. Holes are removable, asymptotes are not. Alright, so here are a couple examples of what these graphs can look like. I just want to bring up, alright, so this one right here, you can't factor the top. The bottom is our issue. So x minus 1 squared is going to be our asymptote. But I want you to, just like we have bouncers for x-intercepts, we also have, to a point, double asymptotes. So what you can see here is there's an asymptote at x equals positive 1. By setting this factor, both of these factors, I guess, equal to 0 and solving. So basically you get a double asymptote. And what's going to happen around those double asymptotes is your left and right hand limits are going to be approaching either both infinity or both negative infinity. So you can see this going, okay, so the limit here, the limit of our function 1 over x minus 1 squared as x approaches 1, we would say, if I said from the left, I would go ahead and say this was infinity. Okay, so it's going towards infinity without bounds, or increasing without bounds. If I approach 1 from the right, of this function, I would also say infinity. So overall, this limit right here, x approaches 1, we can actually say that it agrees, and we can actually say that this whole overall limit approaches infinity. Down here, we would say this limit of our function y as x approaches 1, this would be negative infinity, because the left and right are approaching negative infinity. Alright, so here, if you were to approach the limit as x approaches 1 from the left of this function y, or 1 over x minus 1 squared is, oh shoot, sorry, this is, there should not be a square here. Okay, so sorry. This is just 1 over x minus 1. That is that function right there. And you can see that's our parent inverse function, or parent reciprocal function, just shifted over 1. So what I would say, if we're approaching from the left, this thing right here is going to be equal to negative infinity because it is shooting downward. Okay? And then if I were to say, take this as x approaches from the right of this shifted parent function of ours, we would say this approaches infinity. So overall, this limit, x approaches 1 of our function, this one would be does not exist. They do not agree. Alright, so yeah. Alright, there's your homework. Quick, wasn't it? So this one we're going to say find the vertical asymptotes of the function. So don't forget you're always going to try to factor. I am going to go ahead and factor the top. It's kind of a weird one. So this is that perfect square minus a perfect square. So I'm going to write it like this. Are you ready for this? It's going to be x minus the square root of 2 times x plus the square root of 2. Crazy, I know. Check it if you want. Okay, here I'm going to factor the bottom. It's going to be x minus 2 times x minus 1, because again I'm looking at what are the factors of negative 2, and really there's only either 1 times negative 2 or 2 times negative 1, but then we want to make sure that it adds up to be negative 1 here. And so this does, oops, that should be a plus. So this does get us that. So now you look at this factored form and see, well, nothing crosses out, does it? So fat load of nothing, that did, right? I can't reduce this at all. So on our bottom, what we have is set those factors equal to 0 and solve. And so this one's going to, when we add 2 to both sides, x equals 2. This one, when we subtract 1 from both sides, we get x equals negative 1. So there are our vertical asymptotes, and that is what 7 was asking you. And I will just show you the graph here real quick. Here we have them. Here at our negative 1, it's kind of hard to see on this graph. There is our negative 1 vertical asymptote. Sorry. And then here is our, yeah, sorry. It looks a little funny with our scaling. But here is on right at our 2 mark. So x equals 2, there's our other vertical asymptote. So again, you'd have to be careful for evaluating limits around these areas because they do not exist. So there you have it.